Hey there, welcome to another video. So in this video, we're going to talk about sum and difference formulas, and man, they look crazy, but they're really useful. So a lot of times when we get angles that we want to find an exact solution for, and it's not on a unit circle, this can help us. Also, it helps with some identities, dealing with some stuff in calculus where we might have a couple different angles that we want to put together or separate, so we get some different expressions. So we're going to take a look at what these formulas are, most importantly, how we use them. So when we take a look at sum and difference formulas, basically what that means is if you have a trig function with two angles that are added or subtracted, we can typically break those up if they are sine, cosine, or tangent of whatever two angles we're adding or subtracting. Now, where do they come from? Where these come from is basically a distance formula on part of the unit circle. And tangent comes from comparing these. So tangent of alpha plus beta is how we'd call those two angles, alpha and beta, would say, do you remember that tangent can be represented as sine over cosine? So it really would take sine of alpha plus beta divided by cosine alpha plus beta and really just simplify that. So where these come from are distance formula and comparing sine to cosine. I'm not going to go through and prove where they're from. What I am going to do is take some of the ideas that we have for phase shift of sine compared to cosine and prove it with some of these identities. Mostly I'm going to show you how to deal with stuff like this. So if we have like sine of 105 degrees and they want an exact solution, how in the world do you do that? Because that's not on your unit circle. You go 105 degrees isn't there. So here's something we can do. If we look here, if we can represent that angle as either a sum or a difference of two angles that are on your unit circle, well, then we can break it up. Instead of looking at the sum, we can look at sine of the first part of that angle times cosine of the second part. So alpha and beta is what we call those. So this would be alpha, that would be beta, plus cosine of alpha times sine of beta. And if we can do that, then we can find an exact representation kind of as a workaround instead of looking right at 105 degrees. So let's think of 105 degrees. Can you think of two angles that add up or subtract to 105 degrees, both of which are on your unit circle? You might have a couple solutions, but the easiest one in my mind is 60 degrees and 45 degrees. That would add to 105 degrees, but both 60 and 45 are on your unit circle. Why is it valuable? As soon as we represent 105 degrees in terms of 60 degrees plus 45, we can now use this formula. That's what the sum and difference formulas can be used for. So sine of alpha plus beta now is sine of 60 degrees plus 45 degrees. Just take a look at how the formula works for just a second. It says take a look at your first angle. You're going to take sine of your first angle, cosine of your second angle. You're going to multiply those. Let's do that now. That would be sine of 60 degrees times cosine of 45 degrees. We're just using this is alpha and that is beta. So first one, second one, sine of the first one, cosine of the second one. Let's write that. There's a little bit more to it, isn't there? It says if we have a sine of alpha plus beta, we have sine alpha cosine beta plus cosine alpha sine beta. So that would be cosine of 60 degrees, or the first angle, times sine of 45 degrees, or the second angle. Now let's double check it, but that's going to be really nice. So we looked at this and said 105 degrees, no, it's not on a unit circle. If we want an exact solution, you're going to have to break it up in some way. Well, we noticed that 60 degrees and 45 are both on our unit circle, and they add to 105. So we can represent 105 as 60 plus 45. So when we do that, then we take a look at what one of those sum or difference formulas works. We have sine, we're looking at sine. We have alpha plus beta, or 60 plus 45 degrees. That's this one. Sine of the first, cosine second, plus cosine first, sine second. Sine of the first, cosine second, plus cosine first, sine second. When you take a look at sine and cosine, sine always has the same sign, so plus plus, minus minus. Cosine always has opposite. Plus minus, minus plus. Cosines are both cosine in the first term, both sine in the second. Sine has sines and cosines in the first and the second for both of those. So it's a little bit, it's nice to memorize that a little bit, that your sines are the same for sine, opposite for cosine. I always think about it, sines are the same. Cosine, oh, doesn't have the word sine in it. For my brain, that makes sense that you have different signs up there. We'll get to tangent in just a minute. Now that all those are in a unit circle, we can spend some time to just look that up. So sine of 60 degrees, if you remember sine of 60 degrees, that's the same thing as pi over 3. We're going to get square root 3 over 2. Really helps to have your unit circle handy in this. It's a good thing I do. Cosine 45 degrees says, here's 45 degrees, same thing as pi over 4. Cosine is square root 2 over 2. Cosine 60 degrees, well, that's pi over 3. So you're going to be looking at the same angles in a couple places, aren't you? So we have sine of 60, cosine 60. We have cosine of 45, we're going to have sine of 45. So you're just taking the y and x coordinates, depending on whether you're talking about sine or cosine. You're going to be using both of them. So we've said sine of 60, pi over 3, that's root 3 over 2. Cosine 45, we go, okay, that's square root 2 over 2, the x coordinate. Cosine 60, here's 60 pi over 3 again, that's going to be 1/2. And then sine of 45 is square root 2 over 2 again, right there. If we spend the time to simplify that, that's going to be the square root of 6 over 4, that's the square root 2 over 4. So we get square root 6 plus square root 2 all over 4 because of that common denominator. That's it. That is the exact representation of what that is. So the y-coordinate, that's weird, but the y-coordinate of the point where 105 degrees is on your unit circle would be square root 2 or square root 6 plus square root 2 all over 4. That's what they're talking about when they're asking for an exact solution. That's how to find it. Use sum or difference to represent the angle that you cannot find on a unit circle. Just make sure what you're using, those two angles that are added or subtracted, that those are both on your unit circle. It doesn't really help if you go 105 degrees is 100 degrees plus 5 degrees. What's sine of 100 degrees? I don't know. That doesn't really help a lot, right? Because we want to be able to look those up to find an exact representation like we just did. Well, with sine of pi over 12 is not on our unit circle. We're going to have to come up with something, either a sum that adds to pi over 12 or a difference that gives you pi over 12. Now, I'm not thinking of two angles that add up to pi over 12 really nicely on our unit circle because, well, that denominator is already pretty large and my numerator is pretty small. And so I'm not thinking of two fractions that add up to that very nicely. What I can think of is a couple fractions that subtract to give us pi over 12, like 4 pi over 12 minus 3 pi over 12. Why those ones? Well, if we think about 4 pi over 12 minus 3 pi over 12, 4 pi over 12 will simplify to pi over 3. And 3 pi over 12 will simplify to pi over 4. Both of those are on our unit circle. Now that might take some thought. You might be like, I can't do that right away. No, maybe not. But with some practice and with understanding that what we're looking for are angles on a unit circle that you want to represent this as, it'll come. If your angle is already fairly small, you're probably looking for a difference. If your angle's fairly large, like 105 degrees, you're probably looking for a sum. That's not always the case, but that's a good place to start. So I'm thinking, hey, that's pretty small. Pi over 12 is really a fairly small angle. I'm probably looking for subtraction. Let's think. I want to keep my denominator the same to make it easy. 4 pi over 12, that would simplify. 3 pi over 12 would simplify. Okay, 4 pi over 12 minus 3 pi over 12 would give us pi over 12. We're going to do that. So notice that is still pi over 12. 4 pi over 12 minus 3 pi over 12 is still pi over 12. But when we simplify that, that's going to give us pi over 3. That's going to give us pi over 4. Occasionally I'll have students who ask, why don't you just subtract those and get something simpler? You could, but it would be that. And then you'd be stuck again. So we're purposely unsimplifying so that we can find a couple angles that are on our unit circle. Now that we have, look for the appropriate formula. So we couldn't find that one. We said, let's think about separating this as a sum or a difference. A difference works really nicely and still has some angles on our unit circle. So we're looking at sine. We're not a sum right now, we're a difference. So this is the difference of two angles, alpha and beta, first and second, inside of the sine function. So we're going to use that. That says sine of the first minus the second. Well, okay, that's going to give us sine of the first times cosine of the second, or sine of alpha cosine beta, minus cosine of the first, sine of the second. I always think first and second. That way it's a little bit easier for me to put this in perspective, because that's not really an alpha, it's pi over 3. That's not really a beta, that's pi over 4. So just thinking that through helps me a little bit. So I'm going to write that out. So sine of the first angle, pi over 3. All of our sum and difference formulas for sine have both sine and cosine in both terms. Cosine's first, sine's second. Sine of our sum and difference has sine and cosine in both of them. So I'm going to do sine of first, cosine second. Sine also has the same signs. So plus, plus, and we're going to have minus, minus. So sine of the first, cosine second. Now we're going to do cosine of the first, sine of the second. We also really want to check our work. We're going to double check this on the formula every single time. So I want to make sure that I'm doing it right. We'd have sine of the first angle, I've got that. Cosine of the second angle, I've got that. Minus, I've got a minus sign. It matches signs there. Cosine of the first angle, I've got that pi over 3. Sine of the second angle, I've got that pi over 4. Now I'm going to take my unit circle and find those. So when we find sine of pi over 3, that's actually the same thing as 60 degrees. So that's going to be square root 3 over 2. Cosine pi over 4 is the same thing as 45 degrees. That's square root 2 over 2. Minus cosine of pi over 3, that's the same thing as 60 degrees, so that's going to be 1/2. And sine of pi over 4 is square root 2 over 2. We should be getting pretty good at either memorizing or having the unit circle really handy so that we can find those on there. Most of them, when we're using this, are simple angles because that's how we're intending to be. If you can't find that one, make it easy so that you can. This is going to give us square root 6 minus square root 2 over 4. And as much as we want to simplify that, we can't. We don't have like radicals. You can't simplify the numerator or denominator. You're done. That's as good as you can get on that. So we're going to move on just a little bit, and we're going to talk about cosine of 165 degrees. 165 degrees, that's a pretty big angle. How in the world could we represent 165 degrees as two angles? Well, we'll think about that. That's a large angle. Can you think about some angles that are on the unit circle that add up to 165 degrees? A lot of times we're looking for angles like 45 or 135 if we have numbers end in 5. So automatically I'm thinking either 135 or I'm thinking 45. So 165 and 40, if I take away 45, that would give me like 120. 120 is also on a unit circle. So if I write this as 120 plus 45, that would be two angles on my unit circle that add up to that one. That's going to be much better than trying to mess around with 165 degrees. I'm going to write this as a sum of two angles. Oftentimes it'll be asked, does it matter? Does it matter the order in which you have that? Could you do 45 plus 120? It really doesn't matter because of the way the formulas work. It doesn't really matter what order you have that in. I like the bigger angle first. I don't know why, it's just how it works in my head. What you don't want to do, you don't want to say, well, 135 is on my unit circle. 135 degrees is on my unit circle. So why can't I do 135 degrees plus like 30 degrees? You can. You can do both of them. It's just fine to do that if they're all on your unit circle. So now that we have this represented as a sum, we're going to take a look at the appropriate sum or difference formula. This is cosine. We're looking at cosine. We're saying, hey, I have a sum here. 120 plus 45 is just like that alpha plus beta. How cosines work. Cosine sum and difference formulas has all cosines in the first term, all sines in the second. Basically, cosine first, cosine second. Switch your signs. Sine first, sine second. So that's what we're looking at. Cosine of the first cosine of the second. Cosines always pair your cosines and pair your sines. Sine and sum and difference formulas also have a different sign. So if that's plus there, it's going to be minus there. And then we pair our sines up. So our SINE functions, the sine functions, 120 and 45. Thankfully, those are all on our unit circle. So we're going to take a look and go, okay, cosine of 120 degrees. Well, that is past 90 degrees. That's in your second quadrant. So cosine's going to end up being negative, and that's going to be negative 1/2. Cosine 45 degrees is square root 2 over 2. Minus, if you take a look at sine of 120, remember you're going to be looking at the same angle twice. You're just going to be taking the x-coordinate or the y-coordinate. So for sine of 120, we're going to take not negative 1/2, but square root 3 over 2. Times sine of 45 is square root 2 over 2. And yeah, I'm kind of expecting that at this point we're pretty good at using our own unit circle. I know I pulled mine up the first time just to make sure you understand where I'm looking, especially for our degrees, because we hadn't really done that very often. But at this point, I'm expecting you can look at this and go, cosine 120, yeah, I'm able to find negative 1/2. And for sine of cosine 45 degrees, I'm able to find square root 2 over 2. For sine of 120 degrees, I know it's positive square root 3 over 2. And for sine of 45, I know it's positive square root 2 over 2. So when we simplify this, we'll get negative square root 2 over 4 minus square root 6 over 4. I promise they're not all square root 6s and square root 2s and 4s. It just happens what I gave you here. That's about as good as we can get. That would be the exact representation of what that is. This is weird, but here's an angle. Cosine of that angle is an x-coordinate on your unit circle for that angle. This is the x-coordinate on the unit circle for that angle. The exact x-coordinate, not a representation of it, not an approximation of it, the exact x-coordinate for that. And that's really what this stuff means. So I hope I've made sense so far. We're going to come back with a few more examples. Okay, I just couldn't leave it alone. I wanted to show this to you. So in this example just a minute ago, we had 165 degrees, and I said, you know what pops into my head is 120 and 45. Maybe you didn't think that. Maybe you thought 135 and 30. It's just fine. It'll work out just fine. There's not one particular way to do this. As long as you're using two angles that are on your unit circle that add up or subtract 2, whatever that is, it'll work out just fine. Take a look at it. Here's 135 plus 30. That is 165. Using the same exact formula, cosine first, cosine second, minus sine first, sine second. That's exactly what we're doing here. Cosine of 135 degrees, that's in the second quadrant. That right there is going to be negative square root 2 over 2. The x-coordinate is negative in the second quadrant. You're going to get negative square root 2 over 2. Cosine 30 degrees, well, that's square root 3 over 2. Minus sine 135 degrees. In quadrant 2, sine is positive still. That's where 135 degrees is. The y-coordinate is positive. That's square root 2 over 2, but positive. Times sine 30 degrees, that is 1/2. Can you see that you're going to get exactly the same thing? That's negative square root 6 over 4. That's minus square root 2 over 4. Here's the minus, here's the negative, they're just switched around. It's going to give you exactly the same solution. So I hope that makes sense. It doesn't really matter what you pick as long as it's on the unit circle and adds or subtracts to your value. Then use the appropriate formula and it'll work out just fine. we're going to come back with a couple more examples. Let's take a look at tangent now. So we got tangent of 19 pi over 12. That is obviously not a unit circle. 19 pi over 12 is pretty, well, it's larger than we really are used to seeing, right? We have at least more than pi radians there. It's not more than 2 pi radians, but it's a fairly large angle. Most of the time, not all the time, but most of the time when that happens, try to make this a sum of two angles. So when we have 19 pi over 12, I'm thinking that's pretty big. It's not less than our smallest exact angle like pi over 6. So I'm probably going to be trying to add to that. So I obviously want a denominator of 12, but I want two numbers that simplify that. That's the key, right? Because we want to get stuff that's on a unit circle. If we have a denominator of 12, pick things like 4s and 9s and things like that so that you can actually simplify with that 12. I'm thinking, man, let's see, what would be a good one? Well, or 3, so 12 has a lot of different factors to it. So maybe 3 and 16 sounds like it would work. Because that would give me something over 12 that would simplify. There could be several choices we saw in the last example. So I'm thinking 16 pi over 12 plus 3 pi over 12. Both of those will simplify to something on my unit circle. You might have to play around with a couple of them. So we have 16 pi over 12 plus 3 pi over 12. It's still 19 pi over 12, but it's written as a sum of two different angles. Let's simplify those angles. I chose them in such a way that it would simplify, so that would give us something on the unit circle. So 4 goes into both 16 and 12. Goes in 4 times over 3 times. It's 4 pi over 3. And 3 pi over 12 simplifies to pi over 4. If you saw something different, it's not a problem. Honestly, it's not a problem. You could have done... let's see, 10 pi over 12 and got 5 pi over 6, and 9 pi over 12 and got 3 pi over 4. That's perfectly acceptable. You can totally do that. This is just the first one that came to my head. I don't know why that one, it just did. So 4 pi over 3 and pi over 4. Now we're going to take a look at the appropriate sum or difference. So tangent of two angles being added. That's where we're at right now. Let's take a look at how it works. It says we want to take tangent of the first plus tangent of the second over 1 minus tangent of both of them. Notice the signs here. Same sign on the top on the numerator, different sign on the denominator. Same sign on the top on the numerator, different sign on the denominator for tangents. Keep that in mind. So we'll have tangent first plus tangent second over 1 minus tangent of both of them. That's how I think about it. Tangent first plus tangent second over 1 minus tangent of them both. All that's left to do now is take out the unit circle, take out your table, whatever you want to do, and figure out the exact representations of those, because those are all on our unit circle. We haven't done tangent in a while, so when we take a look at tangent of 4 pi over 3, 4 pi over 3 is right there. Tangent takes y over x. Negative divided by negative is going to give you a positive. We know that tangent is positive in quadrant 3. Square root 3 over 2 divided by 1/2. Negatives cancel there. We end up getting square root of 3. That is square root 3. Tangent of pi over 4, it's quadrant 1. Y over x is going to give us 1. 1 minus, now we multiply both of them. So we already have it though. Notice that we've already got it. We know what that is. That's the square root of 3 because we already looked it up. So that's kind of nice about this. That's the same and that's the same. That's just the square root of 3 times 1. That's honestly as good as we can get. We can write this as 1 plus square root of 3 over 1 minus square root of 3 if you want to do that. It doesn't really super matter. Sometimes you'll see teachers or textbooks rationalize the denominator here. That is appropriate. You can do that. How to do that, if you don't remember it, how to do that is to multiply by the conjugate of the denominator. It takes a little bit of work here. What the conjugate is two terms with a different sign in the middle. So 1 plus square root 3, the conjugate is 1 minus square root 3, and vice versa. This is one of those times when you get that answer and you look in the back of your textbook and it's different and completely different. You go, ugh, got it wrong. You might not have got it wrong. It's just that they don't like to see square roots on the bottom of your fraction. And how to get rid of that is rationalizing. So multiply by the conjugate. You have to distribute the numerator. So what we get is square root 3. Square root 3 times square root 3 is just 3. 1 times 1 is 1, plus square root 3. We just distribute the numerator. Square root 3 times square root 3 is 3. 1 times 1 is 1. 1 times square root 3 is 1 square root 3. The denominator it works just like a difference of squares. So the way that is nice for us is when you distribute, 1 times 1 is 1, sure, but you're going to get square root 3 minus square root 3. That always cancels with conjugates. Your middle terms will annihilate one another. So 1 minus just 3. Square root 3 times square root 3 is 3. Negative square root 3 times positive square root 3 is negative 3. When we simplify all that, we'll have 4, 2 square root 3 over negative 2. Lastly, most of the time we don't like to see negatives on the denominator, so we'll take the negative and distribute it through the numerator. Lastly, hopefully you see it. You can actually simplify this. You could do it here, you could do it here. You can factor out 2, or understand that you can divide every term in a fraction by the same number and end up getting negative 2 minus square root 3. Now, naturally, that looks absolutely nothing like that does. It's because we rationalized it, but that would be a whole lot easier to work with. So hopefully that makes sense to you. We took a look at this and said, that's a larger fraction. Let's make sure it's addition. We use a sum formula for tangent and then simplify what we get out of that. Make sure you rationalize if you got a square root on the denominator. We're going to get something very similar with tangent of 15 degrees, but I really want you to think about this. Think about 15 degrees. 15 degrees is smaller than the smallest angle that's on our unit circle. That would be 30 degrees. So we're probably not going to add to get to 15 degrees. We're probably going to take two larger angles and subtract them to get to 15 degrees. Namely, I'm thinking 60 and 45. Because if I think 60 minus 45, it will give me 15 degrees. So I'm going to write that out. I'm going to think of tangent 15 degrees as 60 minus 45 to give us two angles on the unit circle that we already know and can work with, and that match up with our formula of tangent of two angles being subtracted. Now, let's see if we can do this by understanding the sign manipulations of tangent. Here's what tangent does. Tangent takes your two angles being subtracted, takes both of them on the top being subtracted, tangent of the first minus tangent of the second. Remember, same sign for tangent on the numerator, different sign on the denominator, 1 plus, both of them being multiplied. And that's precisely what this says right here. So when we take a look at that, we're going to get tangent first minus second, so alpha minus beta. Tangent of the first minus tangent of the second, 1 plus tangent of both of them. Notice the signs. Same sign numerator, different sign denominator. Same sign numerator, different sign denominator. Both of them tangent first, tangent second. Both of them tangent first, tangent second. We just subtract on the top, we add on the bottom if we have two angles being subtracted for tangent. So I'm going to take tangent of the first angle at 60 degrees. I know that for tangent on the numerator, my sign is the same. And I need tangent of both of those angles. On my denominator, I have a different sign, so plus on the bottom for this subtraction. And then we just, again, we take tangent of both of those angles. but now we're multiplying them. So we take our unit circle back out, and I suppose I should have it out because we don't really deal with degrees very often. So tangent of 60 degrees, that's going to give us y over x, or the square root of 3. Square root of 3 over 2 over 1/2. 2's are going to cancel. You're going to get the square root of 3. Tangent of 45 degrees, well, that's pi over 4. That's 1. On our denominator, we have 1 plus, but then we're going to have the same thing. It's really nice the way this formula works because you already have those written down. Tangent of 60 degrees is square root of 3 over 2. Tangent of 45 degrees is 1. Sorry, I meant just square root of 3. Just love saying square root of 3 over 2. Just rolls off the tongue. So that's square root of 3, that's 1. We just end up multiplying. So we're going to double check. That's square root of 3, great. Minus, that's 1, cool. 1 plus, we already have that. That was the square root of 3. Times, we already have that. That was 1. You'd also have to rationalize this. Notice something. Your conjugate is based on your denominator. So over there, the conjugate is 1 plus the square root of 3 because that's the opposite sign of your denominator pair of terms. Here you would use 1 minus square root of 3. That's going to be the conjugate of your denominator. And we do exactly the same thing. You do need to multiply both the numerator and denominator by exactly the same thing to multiply by this fancy 1 so as to not change the value of that. But when you distribute, you get 1 minus 3 minus 1 plus square root of 3. Square root of 3 times 1, square root of 3, minus 3, minus 1, and then plus, negative times negative is a positive, plus square root of 3. On our denominator, we're going to get 1 minus square root of 3 plus square root of 3, that's 0, and then minus 3. Something really similar happens. It's just that we have a negative 4 plus 2 square root of 3. Over negative 2. You can simplify right now. If you want to divide everything by negative 2, you totally can. You can factor out 2 or negative 2 and simplify whatever you really want to do. If I take both of these terms and divide by negative 2, we'll get positive 2 minus, positive divided by negative is a negative, negative positive 2 minus square root of 3. Now, think about what that means. What that is the ratio of the y-coordinate to the x-coordinate of the point on the unit circle at that degree measurement. So if you go to 15 degrees, whoop, right there, the y compared to the x will be exactly that value. That's what this is doing. It's just that you can't find it on a unit circle and get an exact value. Most calculators won't do it either. So we need some sort of a workaround. That's where those formulas come in really handy. So what we're going to do now, I'm going to give you one more example like this, then we're going to start working backwards. I'll give you some stuff like that and say, hey, does that fit one of these sum and difference formulas that we can simplify kind of in reverse? All right, last one before we go backwards and then make it a little bit more difficult, do some more challenging math. So secant of negative pi over 12, a lot of students get stumped on this for two reasons. Number one, well, there's a negative angle. And number two, secant is not up there. So there's two things that we need to realize in order to get this right. Number one is that while you can figure out two angles that add or subtract to give you a negative, oftentimes if you have an even or an odd function, it might be easier to deal with that first. So because secant is an even function, if I plug in opposite angles, I get out equal results. So that means this, that secant of negative pi over 12 and secant of positive pi over 12 give me the same thing. Because it's even, I can just treat the inside of that function, that argument, as positive pi over 12. Even functions let you do that. So because secant's even, I can say, just change the sign of your angle and you will not get a different result. Opposite inputs give you equal outputs for even functions, and secant is an even function. Now I'm taking a look at that and going, okay, secant of pi over 12. Pi over 12 we dealt with already. Pi over 12 is a fairly small angle. It's smaller than our lowest thing, which is pi over 6, on the unit circle that has an exact representation, an exact answer on it. So if it's smaller than that, I'm probably going to be subtracting angles to get it. So I'm not looking at two angles that add to pi over 12. Those would both be smaller than pi over 12 and also not on the unit circle. Pi over 12 is below pi over 6. That's smaller than the smallest angle there. So if that's true, I'm thinking I'm going to subtract here. What can I subtract? 4 pi over 12 minus 3 pi over 12. That would give us that pi over 12, and we've seen that already. So we've taken a look, said negative angles, use evenness or oddness for your trig function. That's even. You can change the sign, be just fine. It even rhymes. Now, that's a smaller angle. That's less than pi over 6, the smallest angle for which we have an exact representation. I'm going to be subtracting. So I represent that. This is still pi over 12, but it's simplifiable. This would give us pi over 3. That would give us pi over 4. Now, this is where some students get stuck. They go, great, but that's not up there. So what in the world do I do? Instead of inventing a whole new formula for a sum or a difference of secant, realize that secant and cosine are strongly related. In fact, they're reciprocals. So here's what we're going to do. If we find cosine of pi over 3 minus pi over 4, we work it all the way down, then secant of that will be the reciprocal. So we're going to take a look at cosine instead. Yeah, I know that's not the same, but they're reciprocals of one another. So I'm going to find this one, work it all the way down, reciprocate, and it'll be the answer to that. Why? You need to remember that secant and cosine are reciprocals of one another. Secant is a reciprocal function for cosine. So cosine of an angle gives you something. Secant of that same angle gives you the reciprocal of that something. So if cosine of theta equaled 1/2, secant of that angle gives you 2. And that's exactly how cosine and secant are related. So when we find this, we just reciprocate and we get secant for free. Now let's take a look at what that does for us. Since we've already worked this down to two angles being subtracted inside of cosine, that's going to be that function. So cosine works this way. It has cosines of both angles, opposite of your sine, and then sine of both angles. That's how I remember it. So I'm going to take cosine of both angles. It does not matter the order because multiplication is commutative. It does matter the order when you get to subtracting. Like you can't, sometimes you can't reverse these and get the same thing, so be careful with that. Order of like this, like you can't reverse the 1 and the tangents being multiplied. But these two angles you can, it doesn't really matter. So cosine, I know cosines are paired up. I'm going to have a different sign. So minus yields a plus for my formula, and then sines are together. Sine of both angles. And we're going to double check, always double check that. So I've got cosine pi over 3 minus pi over 4. So cosine of first, cosine second. Got that. Different sign, so for a minus, I'm going to get a plus in my formula. Got that. Then sine first, sine second. Sine first, sine second. It looks really good. Now we take our unit circle out, wherever you may have that, and we figured this out. So cosine of pi over 3, that's going to be 1/2. Times cosine pi over 4 is square root 2 over 2. Plus sine of pi over 3 is square root 3 over 2. And sine of pi over 4 is square root 2 over 2. When we simplify all that, we get the square root of 2 plus the square root of 6 all over 4. Because we get square root 2 over 4, we get square root 6 over 4, common denominator lets us put that in one fraction. Now, that is precisely what the x-coordinate of this angle, that pi over 12, would be on the unit circle. So if you went to pi over 12, your x-coordinate would be square root 2 plus square root 6 all over 4. Now that's not what we're looking for. We're looking for secant. So here's what secant would do. If cosine pi over 3 minus pi over 4 is this thing, then secant of pi over 3 minus pi over 4 is the reciprocal of this. Don't reciprocate these, reciprocate this. Cosine gives you one thing, secant will be the reciprocal of that. Now, it would be great if we were just done, but do you see what has to happen? You got 4 over some junk with square roots in it, and they don't like junk with square roots in it, so you're probably going to rationalize. This is correct, right? This is numerically just fine, but you're probably not going to see that. And so rationalizing takes your denominator and multiplies by the conjugate of that, which means that you're going to multiply by square root 2 minus square root 6. And if we do that, it's just a matter of distributing and simplifying. So 4 square root 2 minus 4 square root 6. Which you cannot combine, by the way. Those do not have like radicals. Your denominator should remove all square roots completely. That's going to be square root 2 times square root 2 is 2. Square root 6 times square root 6 is 6. The middle terms are going to cancel. So we have 2 minus square root 12 plus square root 12. That's done. And then minus 6. So 2 minus 6. We are almost done. Hopefully you see this as well. You can factor out a 4 or a negative 4, or just divide every term by negative 4, which is what I'm going to do. So 4 divided by negative 4 is negative 1 square root 2. Negative 4 divided by negative 4 is positive 1 square root 6. And of course you can make it a little bit nicer by putting square root 6 minus square root 2. It doesn't really matter. What does matter is that you get down that far, because that is actually a lot easier to work with than that with some square roots on the denominator. I hope I've made it very clear on how you can take some angles that are not on unit circle and manipulate them to the point where you can use these formulas to figure out exact representations of those angles when you can't even look up the angles themselves. So that's pretty nice. That's one use of this. What we're going to do now is we're going to come back and we're going to take a look at what would happen going in reverse. We're going to take a look at just a few more examples on how you can use these formulas directly. So namely, how to go backwards, really, because it gets you used to some identities. How to use these things in reverse is really important because they are identities. That means they're not just one-way streets. They go both ways here. So we should be able to say, hey, if it fits this, you can make it even simpler. And that's what this does. So here's the point. If these fit this side perfectly, you can go the other way. So how we do this, we really take a look at the structure of it. If you have sine and cosine together minus another cosine sine together, you're talking about either a sum or a difference for sine. Sum or difference for your sum and difference formulas for your sine. That's right here. So when we take a look at that, we go, all right, well, which one does it fit? Does it fit any of them? So I'm taking a look at the sine of 20 degrees, cosine 80 degrees minus cosine 20 degrees, sine of 80 degrees. I'm noticing the two different functions in both terms, sine cosine, cosine sine. I'm noticing the minus. That's pointing me right here. So there's a minus, there's sine cosine, there's cosine sine. What's that tell us? If we have the same angle here and the same angle here, sine and cosine, cosine sine, and we switch the angle between them and we have a subtraction, here's what we can do. We can take whatever this angle is and subtract it into sine. We can go that way. So this would be the same thing as sine of 20 degrees minus 80 degrees, but it has to be in that order. That's really important. What I mean by that is you can't take this and do sine of 80 degrees minus 20 degrees. The subtraction is not commutative. So the order that this is, where you have 20, 80, 20, 80, that is your first angle, and that is your second angle. It has to, sorry, here, that is your first angle, that is your second angle. It has to be subtracted in that order. So 20 minus 80, not 80 minus 20. Sine of negative 60 degrees. You know, you really could do that. You could take out your unit circle, go negative 60 degrees, and find the y coordinate. You'd be just fine. But you know me, I want to make you use identities. So what about sine of negative 60 degrees? If sine is an odd function, that means that opposite inputs have opposite outputs. That's what odd means for functions. So sine of negative 60 is the same thing as negative sine of positive 60. Remember with odds, if we change the inside sign, we change the function's sign. And sometimes that's very, very valuable. So negative sine of 60 degrees. Well, let's see, sine of 60 degrees, that's like pi over 3. That's going to be a y-coordinate in quadrant 1 of square root 3 over 2. We just have a negative out front giving us negative square root 3 over 2. So the negative here is that negative. This piece is square root 3 over 2. And that's it. That's exactly what this would be representing, is that negative square root 3 over 2. Let's move on to tangent. So tangent of 40 degrees minus tangent of 10 degrees all over 1 plus tangent 40, tangent 10. That looks really like one of these two tangent formulas. Why? Because it had a whole bunch of tangents in it. Let's just figure out which one. All we've got to do is look for the signs. So our signs say we're dealing with a minus and a plus. Here's a minus and a plus. We're going to be using the difference formula for tangent. So minus, plus, here's our first angle, here's our second. We have to subtract them in that order. So tangent of your first angle, tangent of 40 degrees. 40 degrees has to be the first thing that you do when you have tangent of that argument. It's going to be 40 minus the second. So 40 minus 10, not 10 minus 40. So tangent of first minus tangent of second, that is the first minus the second. So we know the signs are the same for tangent, minus and minus, minus and minus. Now tangent of 30 degrees, that's not too bad. You can use your table, you can use your unit circle, memorize it however you can. Tangent of 30 degrees is pi over 6. So we would take the y coordinate, 1/2, divided by the x coordinate, square root 3 over 2. The 2's are going to cancel. We get 1 over the square root 3. Or if you rationalize, the square root 3 over 3. And that's pretty much as good as we can do. I hope I'm explaining it well enough for you to be able to see that we can go both ways on these formulas. It's really important and useful to be able to do that. Okay, last one. I'm hoping that you can look at this and figure out which one of these formulas is represented. We've actually just used it in that example, but you should be pretty familiar with it at this point. Being able to look at it and go, well, wait a minute. All the cosine stuff has cosines and sines paired up. All the sine stuff has sine and cosine mixed up. All the tangent stuff only has tangents in it. So when we take a look and see sines and cosines and sines, we're dealing with a sum or a difference for sine. In this case, we go, well, that's a minus. Sines have the same sign. So minus says, I'm going to be dealing with a difference of two angles. This is the way that I organize in my head. It works for me, maybe it'll work for you, is that I always categorize these as what do they act like in general. Sines always have both sine and cosine in both terms, and they have the same signs for the sum and for the difference. So for us, that's going to create a difference. Also, we have the order. It's really important that we have sine of the first, cosine of the second. That must be your first angle. That must be your second angle. What that means for us is that we would take these things tell us we're dealing with sine. This says it's a difference. Putting it all together says this can all be represented going backwards as sine of the first angle minus the second. That's pi over 12 minus 7 pi over 12. That's negative 6 pi over 12. Now, you can be thinking odd function right now. That's great. You could totally change your sign there. We can also simplify. So 6 pi over 12 is the same thing as pi over 2. So I'm going to do two things right now. 6 pi over 12 is pi over 2. And then because sine is an odd function, I can say opposite inputs are opposite outputs. I can change my sign of my argument and get a sign change for my function itself. So that's pi over 2. Negative angle gives us negative function for odd functions there. Pi over 2 is pretty nice for sine, so that's going to be 1. So this whole thing works down to just negative 1. And that's really all there is to it. I hope that this has made sense so far. I hope that you're really seeing the utility in using this. It's kind of nice. It works really well to be able to deal with some very awkward things. So that's really our introduction to how these sum and difference formulas work. What's going to happen in the next videos, I'm going to come back with some more advanced stuff. We're going to talk about what would happen dealing with sum and difference when we have to find some angles that aren't even representable on a unit circle. And so we're going to do that. We'll talk about some proofs, some kind of cool proofs about about phase shifting for sines and cosines. And lastly, we'll talk about inverses. So inverses as it really works with some of these sum and difference formulas. That's about it. So I hope you've enjoyed the video. I hope you've learned something. We're going to break this up and come back with some more advanced concepts in just a little while. Have a great day.